The universe is expanding, that much is certain. But when astronomers measure how fast it is expanding, the answer depends on where they look. Ancient light from the early universe points to one number, while nearby stars and supernovae point to another. After years of increasingly precise observations, the disagreement still remains. Tonight, this quiet cosmic mystery leads from distant galaxies to the measurements at the heart of modern cosmology. If calm journeys through space and science are enjoyed, please like the video, subscribe to the channel, and settle in as the Hubble tension slowly unfolds. Across the largest scales that can be observed, the universe appears as a vast arrangement of galaxies, galaxy groups, clusters, filaments, and enormous regions containing relatively little matter. These structures do not remain fixed in their separations. On average, galaxies that are not held together by the same local gravitational system become farther apart as cosmic time passes. This gradual increase in separation is described as the expansion of the universe. It is not usually pictured as galaxies simply racing through an otherwise motionless emptiness. Instead, modern cosmology describes the large-scale geometry of space itself as changing with time so that sufficiently distant unbound regions acquire increasing distances from one another. This expansion becomes clearest when astronomers look far beyond the gravitationally connected surroundings of individual galaxies. Inside a galaxy, gravity strongly organizes stars, gas, dust, and dark matter. Within a galaxy group, gravity can also keep neighboring galaxies bound together. The Milky Way and Andromeda belong to such a local system, and their motions are therefore not simple examples of the general cosmic expansion. At much greater distances, however, the collective pattern becomes increasingly smooth. The farther a galaxy lies from an observer, the greater its recession tends to be when averaged over many systems and large enough scales. The relationship between distance and recession is summarized by the Hubble constant. Despite its name, this quantity describes the expansion rate at the present cosmic era rather than a rate that has remained unchanged throughout all of history. The expansion rate evolves as the contents of the universe and their gravitational effects change. Matter tends to slow expansion through gravity, while the component called dark energy is associated with the observed late-time acceleration of cosmic expansion. The Hubble constant, therefore, represents a present-day value within a much longer history. Astronomers commonly express it as kilometers per second for every megaparsec of distance. A megaparsec is about 3 million light-years. This means that the expected recession associated with cosmic expansion grows with distance. A galaxy at one distance participates in a certain amount of recession, while a galaxy twice as distant in the simplest nearby approximation participates in roughly twice that amount. Individual galaxies can deviate because local gravity gives them additional motions, but the large-scale trend remains one of the foundations of observational cosmology. Light carries the evidence for this expansion across immense distances. When light travels through expanding space, its wavelength is stretched. Light emitted at shorter wavelengths can arrive at longer wavelengths, producing cosmological redshift. The effect provides astronomers with a way to describe how much the universe has expanded during the light's journey. A small redshift in the nearby universe is closely related to recession, while very large redshifts require a fuller cosmological description because the expansion history changes during the long travel time of the light. The observable universe is a record of cosmic times. Light from nearby galaxies begins its journey relatively recently in cosmic terms. Light from extremely distant galaxies travels for billions of years before reaching a telescope. Looking outward in distance also means looking backward in time. Yet, the expansion measured today is not obtained by simply watching the edge of the observable universe move. The cosmic horizon is a boundary set by the finite age of the universe, the finite speed of light, and the history of expansion. It is not a material shell surrounding a central location. No special central position is required for cosmic expansion. On sufficiently large scales, observers in different galaxies would describe other distant unbound galaxies as receding in a broadly similar pattern. Homogeneity means that matter is distributed approximately uniformly when averaged over very large regions. Isotropy means that the universe looks approximately similar in different directions when viewed on those scales. Galaxies, clusters, and cosmic filaments create local irregularities, but the broader statistical pattern becomes much smoother. Expansion does not require space to grow outward into a surrounding emptiness. Cosmological models describe distances within the universe changing according to the geometry of space-time. The observable region can therefore grow in the sense that light from previously unreachable regions eventually has time to arrive, while cosmic expansion simultaneously increases the separation between many distant regions. These ideas belong to cosmic geometry rather than to the motion of an outer surface. The present expansion rate matters because it connects several fundamental properties of cosmic history. A different expansion rate changes the relationship between redshift, distance, and time. It affects estimates of how long the universe has been evolving under a given cosmological model. It also influences the inferred scale of distant structures and the interpretation of observations collected across many wavelengths. Measuring the Hubble constant therefore establishes a scale that reaches through much of observational astronomy. Modern measurements are remarkably precise compared with the first attempts to establish cosmic expansion. Early observations reveal the broad relationship between galaxy distance and recession, but distances are difficult to determine, and the first numerical estimates are far from current values. Over decades, telescopes, detectors, stellar physics, and statistical methods improve. The broad conclusion remains secure. The universe is expanding, and that expansion has changed over cosmic time. The difficulty now lies in determining its present rate with enough precision that different observational routes should agree within their stated uncertainties. That agreement has not fully emerged. Measurements tied to nearby astronomical distances tend to favor a higher present expansion rate than values inferred from observations of the early universe interpreted through the standard cosmological model. The disagreement is known as the Hubble tension. Its importance comes not from doubt that expansion exists, but from the precision with which different approaches now describe it. Each method rests on observations that have been repeatedly refined, while the gap has remained difficult to remove through any single known correction. At the outermost level, the situation is quiet but unresolved. The large-scale universe expands. Distant, unbound galaxies follow a systematic recession pattern. Their light records the stretching of cosmic space, and the Hubble constant provides a present-day scale for that expansion. These statements are supported by many independent observations. The remaining difficulty is narrower and more delicate. The universe appears to provide more than one precise route toward its current expansion rate, and those routes do not yet converge on exactly the same result. Far beyond the nearby galaxies, the observable universe contains a background of microwave radiation arriving from every direction. This radiation is known as the cosmic microwave background. It is not produced by stars, galaxies, or ordinary clouds of interstellar gas. It is a relic of an earlier cosmic era when the universe is hot, dense, and filled with a glowing mixture of matter and radiation. The light now reaches telescopes after traveling for almost the entire history of the observable universe, carrying a detailed record of conditions that exist when cosmic structures are still in their earliest stages. At that early time, the universe is very different from the transparent cosmos seen today. Matter is mostly present as a plasma, a hot state in which electrons are not yet permanently bound to atomic nuclei. Photons scatter repeatedly from free electrons, so light cannot travel freely over distances. The environment is therefore opaque as light is scattered inside a dense fog, although the physical process is entirely different. Radiation and ordinary matter remain closely coupled, exchanging energy and responding together to variations in density. As cosmic expansion continues, the universe cools. Roughly 380,000 years after the beginning of cosmic expansion, temperatures fall enough for electrons to combine with nuclei and form neutral atoms, mostly hydrogen and helium. This transition greatly reduces the scattering of photons by free electrons. Light that has been trapped in the hot plasma can then travel through space over distances. The moment is often called recombination, although the name reflects historical terminology rather than a previous period in which the same atoms had already formed. The release of this light marks the surface from which the cosmic microwave background becomes visible today. The radiation is initially much hotter and has much shorter wavelengths than the microwaves detected in the present universe. As space expands during the billions of years that follow, those wavelengths stretch. The radiation cools in step with the expansion until its spectrum corresponds to a temperature a few degrees above absolute zero. Its present form is therefore not a separate kind of light created late in cosmic history. It is ancient radiation transformed by the continuing expansion of space. Across the sky, the cosmic microwave background is extraordinarily uniform. Its temperature differs only slightly from one direction to another. This near uniformity supports the picture of a universe that is smooth on very large scales. Yet, the tiny differences are essential. They appear as subtle temperature variations that trace small differences in the density, motion, and gravitational environment of the early cosmic plasma. Regions that are slightly denser or less dense than average leave patterns in the radiation, preserving information that later becomes connected with the large-scale distribution of matter. Before neutral atoms form gravity and radiation pressure act together in the hot plasma. Gravity draws matter towards slightly denser regions while pressure in the photon-filled material resists compression. The competition creates acoustic oscillations, which are pressure waves moving through the early cosmic mixture. These waves do not sound through ordinary air. They are changes in density and pressure traveling through plasma. Their characteristic scales become imprinted in the cosmic microwave background when photons begin to travel freely. Astronomers examine the sizes and strengths of these patterns across the sky. Instead of treating the background as a perfectly featureless glow, they measure how temperature differences vary over different angular scales. Some patterns span broad areas while others are much finer. The statistical distribution of these variations contains information about the amounts of ordinary matter, dark matter, and other components present in the early universe. It also carries information about the geometry of space and about the physical conditions that govern the growth of the primordial fluctuations. Polarization adds another layer of information. Light can possess an orientation in its electric field, and scattering in the early universe produces weak patterns of polarization in the microwave background. These patterns provide additional tests of the same early physical processes. They help constrain how matter moves in the plasma and how later events alter the path of the radiation. The measurements are difficult because the signals are faint and because microwave emission from the Milky Way and other foreground sources must be separated carefully from the ancient cosmic signal. Space observatories and ground-based instruments map this background with increasing precision. Missions such as NASA's Wilkinson Microwave Anisotropy Probe and ESA's Planck Observatory measure temperature variations across nearly the entire sky. Their observations reveal a pattern that is highly consistent with a universe that begins in a hot, dense state and evolves through expansion. The detailed structure of the microwave background becomes one of the strongest foundations of modern cosmology because many different physical effects are encoded within the same ancient light. The apparent surface from which this radiation arrives is called the last scattering surface. It is not a solid boundary and does not surround the universe as a physical wall. It represents the distant regions where photons last interact strongly with charged matter before traveling freely. Because light requires time to cross space, every direction reveals this early epoch at a distance. The observed sphere is naturally centered on the observer only because observation always looks backward along incoming paths of light. Another observer elsewhere would define a different visible last scattering surface around that location. Small variations within the background are measured at differences of only tiny fractions of a degree in temperature. Their arrangement is statistical rather than a map of individual future galaxies. Slightly denser regions provide seeds from which gravity later builds larger structures, but the microwave image itself belongs to the early plasma. Its patterns describe conditions before mature stars, galaxies, and clusters dominate the visible cosmos. The ancient radiation also passes through intervening matter during its long journey. Hot electrons in galaxy clusters can alter some microwave photons, while gravitational structures can bend their paths slightly. Astronomers model these later effects and foreground emissions so that the primordial signal can be separated as possible. What remains is an unusually precise portrait of a young universe, almost uniform yet marked by delicate variations. Across the sky, this faint microwave glow preserves the physical state of matter and radiation near the time when the cosmos first becomes transparent. The cosmic microwave background does not measure the present expansion rate in the same direct way as a nearby distance measurement. Its light comes from an era only a few 100,000 years after the beginning of cosmic expansion, so the information it carries belongs to the early universe. To obtain a value for the expansion rate today, cosmologists combine that ancient pattern with a mathematical description of how the universe evolves. The result is an inference. It begins with conditions measured in the early cosmos and follows their consequences forward through billions of years of expansion. The most important features in the microwave background arise from acoustic oscillations in the hot plasma before neutral atoms form. Gravity tends to compress matter into slightly denser regions, while radiation pressure resists that compression. The repeated balance between inward gravitational attraction and outward pressure produces a family of waves with characteristic scales. When photons begin to travel freely, the oscillations stop being driven in the same way, and their pattern becomes frozen into the radiation that later reaches telescopes. One characteristic distance becomes especially important. It is called the sound horizon. The sound horizon represents the greatest distance that pressure waves can travel through the early plasma before the universe becomes transparent. Its physical size depends on the expansion rate during that early period and on the amounts of matter and radiation present. Because the relevant physics is well understood, the sound horizon can act as a standard ruler, a scale whose expected physical size can be calculated from the conditions of the young universe. Astronomers do not observe this ruler directly as a line drawn across space. They see its imprint as a preferred angular scale in the temperature pattern of the microwave background. The apparent size of that pattern depends on two broad ingredients. One is the physical size of the sound horizon at the time the radiation is released. The other is the geometry and expansion history between that distant surface and the observer. A ruler of a known size appears larger or smaller depending on the distance through which its light travels and on the geometry of the intervening universe. The microwave background contains more than one acoustic feature. A sequence of peaks appears when the temperature variations are arranged according to angular scale. Their locations and relative heights carry different pieces of information. Some respond strongly to the amount of ordinary matter. Others depend on the total matter density, including dark matter. The overall pattern is also influenced by the initial distribution of primordial fluctuations and by the radiation content of the early cosmos. By fitting all these features together, cosmologists can determine a tightly constrained set of model parameters. The present Hubble constant is one of the quantities derived from that fit, but it is not isolated from the rest. The inference depends on how the model connects early densities, geometry, and later expansion. Within the standard cosmological framework, the physical density of ordinary matter and dark matter helps determine the sound horizon, while the model of later cosmic expansion determines how that ancient scale appears on the sky today. The fitted parameters must satisfy all parts of the observed microwave pattern at once. This interdependence is why the early universe estimate can be very precise. Precision does not come from observing a nearby galaxy with extraordinary certainty. It comes from the large amount of structured information contained in the microwave background and from the restricted way in which the standard model allows that information to evolve. Thousands of measured angular scales contribute to the statistical fit. When the model is fixed, many combinations of parameters are ruled out because they would shift the acoustic features, alter their relative heights, or distort the overall spectrum of fluctuations. ESO's Planck measurements provide one of the most precise full sky maps used for this purpose. Within the standard cosmological model, analyses of the Planck data favor a present expansion rate near the high 60s in kilometers per second per megaparsec. The exact inferred value depends slightly on the data combination and analysis choices, but the central result is stable enough to define the early universe side of the Hubble tension. The uncertainty is small because the microwave background pattern is measured with high precision and because the standard model links its features together tightly. The inference also uses the assumption that the physical laws governing the early plasma are correctly described. Atomic physics determines when electrons and nuclei combine. General relativity describes how matter and radiation influence cosmic expansion and gravitational potentials. The behavior of photons, neutrinos, ordinary matter, and dark matter determines the evolution of fluctuations. Small changes to these ingredients can alter the calculated sound horizon or the later relationship between distance and redshift. For this reason, the early universe value of the Hubble constant is best understood as model-dependent rather than as a purely local reading of expansion. The cosmic microwave background directly constrains combinations of physical quantities at early times. The present expansion rate emerges after those constraints are interpreted within a model of cosmic evolution. If the model accurately describes the universe from the era of last scattering to the present, the infrared value should agree with independent measurements of the present expansion rate. The consistency of the microwave data with the standard model is remarkably strong across many observables. Temperature fluctuations, polarization patterns, and gravitational lensing of the microwave background broadly support the same cosmological picture. This internal agreement makes the early inference difficult to dismiss as a simple measurement error. At the same time, model dependence remains essential to its meaning. A precise result can still shift if the physical assumptions connecting the early and late universe are altered in a way that remains compatible with all relevant observations. The early universe root, therefore, begins with a faint microwave glow and ends with a present-day number only after a long chain of physical reasoning. The ancient plasma sets a characteristic scale. The observed sky reveals the apparent size and statistical structure of that scale. A cosmological model then connects those measurements to the history of expansion. Within that framework, the inferred present rate is tightly constrained, forming one of the two precise values whose persistent disagreement defines the Hubble tension under the model being tested. The standard cosmological framework provides the structure that connects the early universe to its present expansion. It is usually called the lambda-cold dark matter model. Lambda represents the component associated with dark energy, while cold dark matter refers to matter that moves slowly compared with light when large cosmic structures begin to form. The model also includes ordinary matter radiation neutrinos and the geometry of space-time, described by general relativity. Together, these ingredients create a compact description of cosmic evolution from the hot, early universe to the large-scale structure seen today. The framework begins with a universe that is nearly homogeneous and isotropic on very large scales. Matter is not distributed perfectly evenly, but the initial departures from uniformity are small. These slight variations provide the seeds from which later structures grow under gravity. The model assumes that the large-scale behavior of space-time follows general relativity, and that the contents of the universe can be represented by components with different densities and pressure properties. Each component influences how quickly expansion changes with time. Radiation dominates the energy budget at very early times. As the universe expands, the energy density of radiation decreases rapidly because the number of photons is spread through a larger volume and their wavelengths are stretched. Matter behaves differently. Its density also decreases as space expands, but not as quickly as radiation. Eventually, matter becomes the dominant component affecting the expansion and the growth of gravitational structure. Much later, dark energy becomes increasingly important because its density changes much more slowly than the density of matter. In the simplest version of the model, cold dark matter plays a central role in this history. It does not emit or absorb ordinary light, but its gravitational influence appears in many astronomical observations. In the standard model, dark matter begins gathering around slightly denser regions, while ordinary matter remains strongly coupled to radiation during the early plasma era. After atoms form and radiation travels freely, ordinary matter can fall more effectively into the gravitational structures already developing in the dark matter distribution. Over time, these regions grow into the large cosmic web of galaxies, groups, and clusters. The term cold describes the behavior of dark matter rather than its temperature in the ordinary everyday sense. Cold dark matter moves slowly enough during structure formation that it can preserve small-scale density variations. A population of particles moving close to the speed of light would erase more of those small structures. Observations of the distribution of galaxies and the cosmic microwave background are broadly consistent with a dominant dark matter component that behaves as cold matter on cosmological scales. Its microscopic identity remains unknown, but the standard cosmological model describes its large-scale gravitational effects without requiring a specific particle to be identified. Lambda represents the simplest description of dark energy. In general relativity, it can appear as a cosmological constant, an energy density associated with empty space that remains constant as the universe expands. When matter becomes sufficiently diluted, this component causes the expansion to accelerate. Observations of distant supernovae and other cosmological probes support the conclusion that the recent expansion is accelerating. Within the standard framework, a cosmological constant provides a simple explanation that fits a wide range of measurements. The model also includes ordinary baryonic matter, the material associated with protons and neutrons. Stars, planets, gas dust, and living matter belong to this category. Ordinary matter forms only a minority of the total cosmic energy budget. Even though it produces most of the light seen by telescopes, its gravitational contribution on the largest scales is smaller than that of dark matter. The abundance of ordinary matter can be constrained through both the cosmic microwave background and the production of light elements in the early universe. Neutrinos provide another small but significant component. These particles interact weakly with ordinary matter and travel rapidly during much of cosmic history. Their masses are small, yet their collective behavior affects the growth of structure and the detailed pattern of the microwave background. Cosmological measurements can therefore place limits on their total mass and abundance. Within the standard framework, neutrinos are included in a way that remains consistent with particle physics and astronomical observations. Spatial geometry is another essential element. Measurements indicate that the universe is very close to spatially flat on the largest scales. Flatness does not mean that space-time contains no curvature near stars, galaxies, or black holes. It refers to the average geometry of enormous cosmic distances. In a spatially flat cosmological model, the total energy density is closely related to the expansion rate through the equations of general relativity. This relationship helps connect the measured contents of the universe to its expansion history. A small set of parameters controls the standard model. These include the densities of ordinary matter and dark matter, the present expansion rate, the properties of the initial fluctuations, and the optical effects associated with the later ionization of cosmic gas. When observations are analyzed, the parameters are adjusted together until the predicted patterns match the measured data. Because one parameter can affect several observables at once, the resulting constraints depend on the internal consistency of the entire framework, rather than on a single measurement. This compactness is one reason the model is powerful. With relatively few parameters, it describes the cosmic microwave background, the broad distribution of galaxies, the abundance of light elements, gravitational lensing statistics, and the accelerated expansion of the recent universe with substantial success. No alternative framework has yet replaced it while matching the same range of observations with comparable simplicity and precision. This coherence also limits how freely any single parameter can change. Raising the present expansion rate can alter distances, ages, and infer densities, so other parameters must shift together while preserving observed cosmic patterns. The same compactness also makes discrepancies important. If a measured quantity refuses to fit, while the rest of the framework remains successful, the source may lie in an unrecognized observational effect, an incomplete treatment of known physics, or a limitation of the model itself. The standard framework, therefore, acts as both a successful description and a demanding consistency test. Its assumptions determine how ancient measurements are translated across cosmic time, and its internal relationships set the reference against which disagreements in the expansion rate are judged. Long after the cosmic microwave background is released, the pressure waves of the early plasma no longer travel through matter in the same way, but their scale does not disappear. The pattern remains embedded in the distribution of material. Regions separated by a characteristic distance have a slightly enhanced probability of containing matter, leaving a faint, statistical imprint that survives as galaxies form and gather into the cosmic web. This feature is known as baryon acoustic oscillation, or BAO. It provides a way to follow cosmic expansion across the long interval between the ancient microwave background and the comparatively nearby universe. The origin of the scale lies in the same early mixture of radiation and matter that produces the acoustic features in the microwave sky. Before neutral atoms form ordinary matter and photons interact strongly, a small region with slightly greater density draws material inward through gravity. The compressed photon-filled plasma develops pressure that pushes outward a wave of density, therefore travels away from the original concentration. Dark matter does not participate in the photon pressure. In the same way, so much of it remains concentrated nearer the initial gravitational region, while the wave in ordinary matter moves outward. When the universe becomes transparent, photons begin traveling freely. The pressure support that drives the outward wave weakens sharply. Ordinary matter is left with a small preference for two locations, the central region associated with the original concentration and a surrounding scale reached by the acoustic wave. Gravity then continues building structure for billions of years. Galaxies do not form as neat, spherical shells around single centers because countless primordial fluctuations overlap and evolve together. Instead, the old acoustic scale survives statistically in the separations among enormous numbers of galaxies. In present-day moving coordinates, this characteristic scale is roughly 150 megaparsecs, or close to 500 million light-years. Co-moving distance is a way of describing separation after factoring out the overall expansion of the universe, allowing the large-scale pattern to be compared across different epochs. The BAO feature is extremely subtle. A map of galaxies does not display a visible repeating grid. It appears only after astronomers measure the positions of vast numbers of galaxies and determine how frequently. Different pairs occur at different separations. This statistical measurement is called the correlation function in one common form. Another method examines the same clustering information through a power spectrum, which describes how strongly matter is distributed across different spatial scales. Both approaches reveal the preferred acoustic scale. The feature acts as a standard ruler because its physical origin is tied to well-understood processes in the early universe. Once the ruler is calibrated, its apparent size at later cosmic times provides information about distances and expansion. Galaxy surveys build three-dimensional maps by measuring positions across the sky and determining redshifts from spectra. A spectrum spreads light according to wavelength and reveals recognizable features produced or absorbed by atoms. When these features arrive at longer wavelengths than expected, their shift provides a measure of cosmological redshift. Combining sky position with redshift allows astronomers to map galaxy clustering over immense volumes and to divide the observations into different periods of cosmic history. The BAO ruler can be measured both across the line of sight and along it. Across the sky, its apparent angular size constrains distances at a particular redshift. Along the line of sight, its extent in redshift constrains the expansion rate at that epoch. These two orientations provide related but distinct information. Together they create a geometric test that depends much less on the intrinsic brightness of galaxies than methods that use luminous objects as distance indicators. Different kinds of astronomical objects trace the matter distribution at different cosmic times. Bright galaxies provide dense samples over substantial volumes. Luminous red galaxies can be identified across large distances because their spectra are distinctive. Emission line galaxies trace other environments and extend the map to earlier epochs. Quasars powered by active galactic nuclei remain visible across still greater distances. At sufficiently high redshift patterns of absorption in the light of distant quasars reveal intervening hydrogen gas, allowing the acoustic scale to be measured even where ordinary galaxy surveys become less effective. Modern spectroscopic programs gather millions of these tracers. The dark energy, spectroscopic instrument, or DASI, measures the spectra of galaxies and quasars across a large fraction of the sky, producing a three-dimensional view of cosmic structure over many billions of years. Its BAO measurements extend and sharpen earlier work from large galaxy surveys. The resulting distance measurements follow the expansion history across several epochs rather than describing only a single moment. The acoustic ruler is not entirely independent of early universe physics. Its calibrated length depends on conditions before and around the time when ordinary matter separates dynamically from radiation. Changes in the early expansion rate, radiation content, or other physical ingredients can change the size of the sound horizon. For this reason, BAO observations often constrain distances relative to the sound horizon, rather than providing an absolute distance scale by themselves. When combined with information that fixes the ruler's true size, they become a powerful measure of cosmic geometry. This distinction is important in discussions of the expansion rate. BAO data can show how distances change with redshift with great precision, yet the conversion to an absolute present expansion rate depends on how the acoustic ruler is calibrated. A calibration derived from early universe physics links BAO naturally to the cosmic microwave background. Other approaches can combine BAO with additional information to reduce dependence on particular assumptions. The observed clustering feature itself remains a measured property of the galaxy distribution, while the cosmological interpretation depends on the framework used to translate that feature into absolute distances. Across intermediate cosmic time, BAO measurements create a bridge of scale rather than a direct photograph of expansion. The ancient pressure wave leaves a faint preference in matter separation. Galaxies inherit that statistical pattern as structure grows. Large surveys recover the preferred distance from millions of objects spread through enormous volumes. The ruler then traces how cosmic distances change from one epoch to another. Within the standard cosmological framework, these measurements broadly support an expansion history that connects the early universe with the later cosmic web, while preserving enough independence to test whether that connection remains internally consistent. Across the more recent billions of years of cosmic history, one of the most important tools for tracing expansion comes from the explosions of certain stars. These events are called Type Ia supernovae. They are extraordinarily luminous and can be detected across vast distances, allowing astronomers to compare how bright they appear with how bright they are expected to be intrinsically. That comparison provides a way to estimate distance. When distance is combined with redshift, the changing relationship between the two reveals how cosmic expansion behaves over time. A Type Ia supernova occurs in a system containing a white dwarf, the dense remnant left after a star similar in mass to the Sun finishes its normal nuclear burning life. In one broad class of scenarios, the white dwarf gains matter from a companion star. In another, two white dwarfs interact or merge. The detailed pathways can differ, and research continues to refine how frequently each route occurs. What matters for cosmology is that the resulting explosions share enough physical similarity for their luminosities to be standardized with high precision. They are not perfectly identical candles. Their peak brightness varies. Astronomers therefore describe them more accurately as standardizable candles. Observations show that the shape of a supernova light curve, which records how brightness changes with time, is related to its intrinsic luminosity. Supernovae that fade more slowly after maximum light tend to be intrinsically brighter than those that fade more quickly. Their color also provides information that helps account for dust intrinsic variation and other effects. By applying empirical corrections based on these measured properties, astronomers reduce the scatter in their estimated luminosities. Once the intrinsic luminosity is standardized, the observed brightness gives a luminosity distance. This distance is defined through the way light spreads and is affected by cosmic expansion. A more distant supernova appears fainter, but the relation is not simply the inverse square behavior familiar from a static Euclidean space. Expanding spacetime stretches photon wavelengths, changes their arrival rate, and alters the geometric relation between emitted and observed light. Cosmological models account for these effects when connecting measured brightness to distance. Redshift provides the other side of the comparison. Spectra from the supernova itself, or more often from its host galaxy, reveal how much the emitted light has been stretched. A large sample of Type Ia supernovae distributed across different redshifts, therefore, creates a map of distance against cosmic epoch. Nearby events represent relatively recent expansion, while more distant events preserve information from earlier times. The pattern across many supernovae reveals whether expansion has been slowing, remaining steady, or accelerating. During the late 20th century, two independent research teams used distant type Ia supernovae to test the expected behavior of cosmic expansion. At the time, a universe dominated by matter would be expected to expand more slowly as gravity acts over time. Instead, the distant supernovae appear fainter than such a decelerating model predicts. Their inferred distances are larger. The most successful interpretation is that cosmic expansion has accelerated during the more recent history of the universe. This discovery changes the standard picture of cosmic contents. A component with sufficiently negative pressure can produce accelerated expansion within general relativity. In the simplest model, that component is represented by the cosmological constant associated with dark energy. Supernova observations do not directly identify the physical nature of dark energy. They reveal the distance redshift relation that indicates acceleration. Other cosmological measurements are needed to determine how this component fits with matter geometry and the earlier universe. The supernova method is especially valuable because it probes expansion in a different way from the cosmic microwave background. It does not begin with an early acoustic scale and evolve a cosmological model forward over nearly the entire age of the universe. Instead, it measures relative luminosity distances through the more recent cosmos. However, supernovae alone do not usually determine an absolute value of the Hubble constant with maximum precision, because their intrinsic luminosity scale must be anchored. Without an absolute calibration, they constrain the shape of the expansion history very well, while leaving an overall distance scale partly undetermined. Careful calibration is therefore central. Nearby type Ia supernovae can occur in galaxies whose distances are measured through other methods. When the host distance is known independently, the true luminosity of the supernova can be calibrated. That calibrated luminosity can then be applied to more distant events. Large samples reduce statistical uncertainty, but systematic effects remain important because even small biases in brightness can shift infrared distances. Dust in host galaxies can dim and redden supernova light. The properties of the stellar population can vary between galaxies. The chemical composition and age of the progenitor environment may influence explosion properties in subtle ways. Selection effects can favor the discovery of brighter events at larger distances. Telescope filters, detector responses, and photometric calibration must remain consistent across observations taken with different instruments. Modern analyses model these effects carefully and compare subsamples to test whether hidden trends remain. Another challenge comes from the fact that peculiar velocities matter most nearby. A galaxy can move because of local gravitational attraction in addition to participating in cosmic expansion. For very nearby supernovae, this local motion can represent a significant fraction of the measured recession speed. At greater distances, the expansion signal dominates more strongly. Analyses therefore account for velocity fields and choose redshift ranges that balance calibration quality against the influence of local motions. Despite these complications, Type Ia supernovae remain one of the most successful probes of late cosmic expansion. Their collective brightness pattern strongly supports an accelerating universe and provides a detailed record of how expansion changes over the recent billions of years. The method gains power from repetition because each supernova contributes 1 point to a broad statistical relation rather than carrying the entire conclusion alone. Within this recent cosmic layer, the expansion history becomes visible through fading, stellar explosions scattered among distant galaxies. Their light curves provide standardized luminosities, their spectra provide redshifts, and their apparent brightness provides distance information. Together they trace the late-time geometry of the universe with precision. The measurements establish the changing shape of recent expansion, while the absolute scale still depends on how the nearby luminosity of these supernovae is anchored. It remains a measured record of late cosmic expansion across time. The local distance ladder begins in the part of the universe where individual stars can be measured with enough detail to establish absolute distances. Unlike methods that infer the present expansion rate from conditions in the early cosmos, the distance ladder builds outward from nearby objects whose distances can be determined through geometry. Each rung calibrates the next. The chain eventually reaches galaxies far enough away that their recession is dominated by cosmic expansion rather than by local gravitational motion. The first requirement is a reliable geometric anchor. One of the most fundamental techniques is parallax. As Earth moves around the Sun, a nearby star appears to shift slightly against more distant background stars. The apparent angle of this shift depends on distance. A larger parallax corresponds to a nearer star, while a smaller parallax corresponds to a more distant one. Because the size of Earth's orbit is known, geometry converts the measured angle into an absolute distance without requiring knowledge of the star's intrinsic brightness. Space observatories have greatly improved parallax measurements. ESA's Gaia mission measures the positions and motions of enormous numbers of stars with exceptional precision. These measurements allow astronomers to determine distances to many nearby stars that are also useful as luminosity calibrators. Parallax remains difficult at large distances because the apparent angular shift becomes extremely small, so it cannot by itself reach the galaxies needed for a precise measurement of the Hubble constant. Its role is to establish the lower rungs of the ladder. Once a class of stars has been calibrated geometrically, its intrinsic brightness can be used to estimate distances farther away. The most important example in the traditional local ladder is the Cepheid variable. Cepheids pulsate regularly, becoming brighter and fainter over periods ranging from days to weeks. Their pulsation period is closely related to their intrinsic luminosity. A Cepheid with a measured period can therefore be assigned an expected absolute brightness after the relation is calibrated using nearby Cepheids with independently known distances. The difference between intrinsic and observed brightness then reveals how far away the Cepheid lies after corrections for dust and other effects. Because Cepheids are luminous, telescopes can detect them well beyond the Milky Way. This extends the ladder from the immediate stellar neighborhood into nearby galaxies. Some of those galaxies contain type Ia supernovae. When both Cepheids and a recent or well-recorded supernova are present in the same host galaxy, the known Cepheid distance provides an absolute calibration for the supernova's luminosity. This overlap is crucial. A type Ia supernova can be seen at much greater distances than an individual Cepheid, but its absolute luminosity must first be established. The host galaxies create the connection between the stellar rung and the supernova rung. Once supernova luminosities are calibrated in nearby hosts, astronomers can apply that calibration to supernovae in much more distant galaxies. Those distant events provide the final extension needed to compare absolute distance with redshift in the smooth Hubble flow. The term Hubble flow describes the large-scale recession produced by cosmic expansion. Nearby galaxies do not follow it perfectly because gravitational interactions produce peculiar velocities, meaning motions relative to the average expansion. A galaxy may fall toward a cluster or move within a group at hundreds of kilometers per second. At small distances, such motion can strongly affect the observed redshift. At larger distances, the recession associated with expansion becomes much greater, reducing the fractional importance of these local velocities. For this reason, the ladder does not determine the Hubble constant from the nearest supernova hosts alone. Nearby hosts are used for luminosity calibration, while more distant supernovae are used to measure the expansion relation. The calibrated absolute brightness tells astronomers how far away those supernovae are. Their host galaxy redshifts indicate the amount of recession. Across a large enough sample, the slope of the distance redshift relation provides the present expansion rate. Every rung must preserve the scale established below it. An error in the geometric anchor can change the calibrated luminosity of nearby Cepheids. That shift can then change the inferred distances to supernova hosts, alter the calibrated luminosity of type Ia supernovae, and finally change the Hubble constant. The chain is therefore powerful but sensitive. Precision improves when multiple independent anchors are used and when the same calibrations are tested with different instruments, wavelengths, and stellar populations. Astronomers also try to observe different rungs with the same telescope when possible. Using a single instrument reduces the need to transfer brightness measurements between detectors with different responses. Observations in near-infrared light can lessen the effects of interstellar dust and can reduce some forms of variation among Cepheids. High angular resolution helps separate a target star from neighboring stars whose light might otherwise blend with it and make it appear brighter than it truly is. Crowding becomes increasingly important as galaxies become more distant. A Cepheid that appears isolated nearby may occupy a dense region. When seen at lower angular resolution, light from nearby stars can enter the same measured image area. If this blending is not corrected, the Cepheid can seem too bright, making its host galaxy appear too close. Because the Hubble constant depends on the absolute distance scale, even small systematic brightness shifts deserve careful attention. The local distance ladder is therefore not a single measurement but a linked calibration system. Geometry establishes nearby distances. Calibrated stars extend the scale into other galaxies. Supernova hosts connect those stellar distances to far brighter explosions. Distant supernovae then reach deeply enough into the expanding universe for recession to dominate local motion. Each step is observed separately, yet all steps must agree for the final expansion rate to be reliable. Within this local region, the Hubble tension takes on a concrete form. The ladder yields a present expansion rate that is generally higher than the value inferred from the early universe within the standard cosmological model. The disagreement does not arise from one isolated object. It emerges after many geometric measurements, many variable stars, many host galaxies, and many supernovae are linked into a common scale. The strength of the method lies in that chain, while the continuing challenge lies in ensuring that no small calibration effect accumulates across its successive rungs. The construction rests on repeated measurements that connect local geometry with large-scale recession precisely. Cepheid variable stars occupy one of the most important positions in the local distance ladder because their changing brightness follows a regular physical pattern. These stars expand and contract through repeated pulsations, causing their light output to rise and fall over periods that can be measured precisely. The key property is the relation between pulsation period and intrinsic luminosity. Cepheids with longer periods are generally more luminous than Cepheids with shorter periods. Once this relation is calibrated, the observed period of a Cepheid provides an estimate of how much light the star truly emits, and comparison with its apparent brightness then gives its distance. The relation emerges from the internal structure of the star. A Cepheid is an evolved massive star that has entered a stage in which its outer layers become unstable to pulsation. In a particular temperature range, helium in the stellar envelope changes its ionization state in a way that temporarily traps and releases radiation. When the outer layers compress, opacity can increase and heat becomes trapped. Pressure then rises and pushes the layers outward. As they expand and cool, opacity decreases, radiation escapes more freely, and gravity draws the material inward again. The pulsation period reflects the star's size, density, mass, and internal structure. Larger and more luminous Cepheids generally pulsate more slowly, creating the period luminosity relation that makes them useful as distance indicators. Astronomers measure a star over many nights or across repeated telescope visits and build a light curve showing how its brightness changes with time. Calibration is the essential step. A period luminosity relation does not provide an absolute distance unless the luminosity scale is tied to Cepheids whose distances are known independently. Parallax measurements supply one route. Nearby Cepheids can have their small positional shifts measured as Earth or an observatory changes position around the Sun. The resulting geometric distances establish how luminous stars of particular periods actually are. Cepheids in nearby stellar systems can provide additional anchors when those systems have distances determined through other geometric methods. The Large Magellanic Cloud is especially useful because it contains many Cepheids at nearly the same distance from Earth. It is a neighboring satellite galaxy of the Milky Way, so large samples can be studied with relatively little distance variation among individual stars. Precise geometric measurements of eclipsing binary stars provide an independent distance to the galaxy. Cepheids observed there can then help define the slope and 0 point of the period luminosity relation across a broad range of pulsation periods. The chemical composition of a Cepheid also matters. Astronomers use the term metallicity for the abundance of elements heavier than hydrogen and helium. Differences in metallicity can alter stellar opacity, temperature, color, and luminosity, producing small changes in the relation used for distance measurement. Because Cepheids in the Milky Way, the Large Magellanic Cloud, and distant galaxies do not all share the same composition, analyses include corrections for this effect. The size of the correction is measured observationally and compared with predictions from stellar models. Dust introduces another complication. Interstellar grains absorb and scatter some of the visible light traveling from a Cepheid, making the star appear fainter and redder than it would without dust. If this dimming were ignored, the infrared distance would be too large. Observations at multiple wavelengths help estimate the amount of extinction. Near-infrared light is affected less strongly by dust than visible light, so modern distance ladder programs often place substantial emphasis on infrared measurements. The shape of the telescope image also becomes important when Cepheids are observed in distant galaxies. A telescope does not record a star as a perfectly isolated point. Its light spreads across a small image pattern determined by the optics and detector. In crowded stellar fields, neighboring stars can contribute additional light to the same measured region. This blending can make a Cepheid appear brighter, causing its galaxy to seem closer than it really is. High angular resolution artificial star tests and careful image modeling are used to estimate and correct this effect. Space telescopes provide major advantages for these measurements. The Hubble Space Telescope avoids atmospheric blurring and can resolve Cepheids in galaxies far beyond the local group. It has therefore played a central role in connecting nearby geometric anchors to galaxies that host well-observed Type Ia supernovae. More recently, the James Webb Space Telescope has provided observations at longer infrared wavelengths and with different detector characteristics, allowing astronomers to examine some of the same Cepheids with an independent instrument. Comparisons between Hubble and Webb observations are useful because systematic errors can depend on instrument design, wavelength, or image resolution. If crowding in Hubble images were producing a large hidden bias, sharper infrared observations could reveal a shift in measured Cepheid brightness. Current comparisons generally find broad agreement between the two observatories for the stars and galaxies examined, although calibration work continues. These cross-checks reduce the range of simple explanations that could remove the local expansion discrepancy through Cepheid photometry alone. Cepheids are also separated into different populations because not every pulsating star follows the same relation. Classical Cepheids, which are relatively young and massive, are the primary objects used in the modern extragalactic distance ladder. Other pulsating stars can resemble them in some measurements but belong to different evolutionary populations and have different luminosity relations. Careful classification prevents these groups from being mixed in a way that would bias distances. The final Cepheid distance to a galaxy is built from many individual stars rather than from a single object. Each star has measurement noise, intrinsic variation, dust effects, composition differences, and possible contamination from nearby sources. Large samples allow these influences to be modeled statistically. Outliers can be identified through predefined criteria, while the overall relation is fitted across many galaxies and compared with the same calibrated relation established in the anchor systems. Within this stellar layer of the distance ladder, the essential measurement remains simple in principle. A Cepheid's rhythm reveals its intrinsic luminosity, and its apparent brightness reveals how far its light has traveled. Precision comes from careful work on calibration, metallicity, dust crowding, classification detector response, and geometric anchors. Cepheids, therefore, form a tested bridge between nearby geometry and the distances of galaxies containing Type Ia supernovae, carrying the absolute scale of the local universe outward one pulsating star at a time. The tip of the red giant branch provides an independent way to measure distances to nearby galaxies using old, low-mass stars rather than young Cepheid variables. As stars similar in mass to the Sun age, they eventually exhaust hydrogen in their central regions and begin burning hydrogen in a shell around an inert helium core. Their outer layers expand and cool, and the stars move upward along the red giant branch on a diagram of brightness and color. During this stage, the helium core becomes increasingly dense while the star grows more luminous. The rise does not continue indefinitely. In low-mass red giants, the helium core becomes supported partly by electron degeneracy pressure, a quantum mechanical effect. that does not depend strongly on temperature, helium accumulates until the core reaches conditions where helium fusion begins rapidly. This event marks the end of the star's ascent along the red giant branch. Because stars of similar old populations reach this transition at nearly the same core mass, their maximum luminosity before helium ignition is relatively uniform, especially when observed at carefully chosen wavelengths. Astronomers call this sharp upper boundary the tip of the red giant branch, or TRGB. In a well-populated stellar system, a graph of the number of stars against brightness shows a noticeable change at the luminosity where red giants stop accumulating. The position of this edge can be measured statistically from many stars. Once its absolute luminosity is calibrated, the difference between its known intrinsic brightness and its observed brightness provides the distance to the galaxy. The method works best in regions dominated by older stars. Astronomers often observe the outer halos of galaxies where crowding is lower and young stellar populations are less common. These environments contain large numbers of red giants while reducing contamination from bright young stars' dust and complex star-forming regions. The relative simplicity of the stellar population helps make the tip easier to identify and reduces some of the systematic effects that complicate measurements in crowded galactic disks. The brightness of the tip is not perfectly identical in every stellar population. Chemical composition influences stellar color and luminosity, particularly at visible wavelengths. Metallicity, meaning the abundance of elements heavier than hydrogen and helium, changes the opacity and temperature of red giant atmospheres. Modern calibrations, therefore, use color information or select wavelength bands where the luminosity depends less strongly on composition. This treatment allows the same basic stellar transition to be compared across different galaxies with greater consistency. Dust is often a smaller problem for halo red giants than for Cepheids, located in active star-forming regions, although it cannot always be ignored. Foreground dust in the Milky Way can still dim the observed stars, and some galaxies contain diffuse material even far from their centers. Extinction maps and multi-band observations help correct these effects. Because the method uses many stars rather than one isolated object, statistical patterns can reveal whether the measured edge is stable across different parts of a galaxy. Calibration again determines the absolute scale. Nearby, red giants with accurate geometric distances can help establish the luminosity of the tip. Stellar systems whose distances are known through independent geometric techniques provide another route. The Large Magellanic Cloud is useful because it contains extensive old stellar populations and has a well-measured distance. Nearby galaxies with precise geometric anchors can also contribute to the calibration. Different analyses may adopt somewhat different anchor combinations, photometric systems and procedures for identifying the stellar edge. These choices matter because the tip is found through data analysis rather than by labeling a single star. Real stellar populations contain asymptotic, giant branch stars, unresolved companions, photometric noise, and stars spread across a range of metallicities. Astronomers use edge detection methods or statistical models to locate the sharp change in the luminosity distribution. The exact treatment of stellar selection, color cuts, image crowding, and background contamination can shift the measured results slightly. Independent teams therefore test multiple procedures and compare results across different galaxies. The TRGB method reaches far enough to measure distances to some galaxies that have hosted Type Ia supernovae. This makes it possible to calibrate supernova luminosities without using Cepheids as the intermediate stellar rung. When these calibrated supernovae are used to establish the local expansion scale, the resulting Hubble constant has historically shown some dependence on the adopted calibration and analysis. Several TRGB studies have found values lower than many Cepheid-based determinations, while others have obtained values closer to them. The differences have narrowed as calibration samples and photometry improve, but a single universally accepted TRGB value has not replaced the broader range of results. Other stellar indicators provide additional checks. Mirror variables are cool, evolved stars that pulsate over much longer periods than Cepheids. Their periods are related to luminosity, particularly in infrared light, allowing them to serve as distance indicators in galaxies where suitable populations can be resolved. Because Miras belong to older stellar populations than classical Cepheids, they occupy different galactic environments and have different sources of systematic uncertainty. Another method uses carbon-rich stars in a phase known as the asymptotic giant branch. A subset, sometimes called J-region asymptotic giant branch stars, can show a relatively narrow luminosity distribution in near-infrared observations. Their usefulness as precision distance indicators is still being actively tested and calibrated. They offer a potentially valuable comparison because their stellar physics ages and observational environments differ from those of both Cepheids and red giant branch stars. Observations with space telescopes are especially useful because stable imaging and infrared sensitivity can separate crowded stellar fields while placing several indicators on closely related photometric systems across the same host galaxies directly. Independent stellar indicators are valuable precisely because they do not share every source of uncertainty. Cepheids depend strongly on pulsation physics and young stellar environments. The red giant branch depends on the evolution of old, low-mass stars and on locating a sharp luminosity boundary. Miras depend on long-period pulsation and cool stellar atmospheres. Agreement among these methods strengthens confidence that the local distance scale is not controlled by one particular kind of star. Differences, when they appear, identify where calibration and stellar modeling require closer attention. Across these old and intermediate age stellar populations, the distance scale is tested through distinct physical clocks and luminosity features rather than through a single shared assumption. At the base of the local distance scale, astronomers seek measurements that depend as little as possible on assumptions about stellar luminosity. These measurements are called geometric anchors because distance is obtained from geometry, orbital motion, or light travel relationships rather than from how bright an object is expected to be. Their role is to fix the absolute scale of nearby space. Once that scale is established, variable stars and other standardizable objects can carry it outward into galaxies far beyond the reach of direct geometry. Parallax is the most familiar geometric method. As Earth travels around the Sun, a nearby star is observed from slightly different positions in space. Against more distant background sources, the star appears to shift by a tiny angle. The size of that angle decreases as distance increases. Because the diameter of Earth's orbit is known, the distance follows directly from the measured displacement. No model of stellar brightness is required. The difficulty lies in measuring angles that become extraordinarily small for distant stars. Modern space astrometry has transformed this task. ESA's Gaia mission repeatedly measures the positions of stars across the sky, allowing their parallaxes and proper motions to be separated from one another. Proper motion is the apparent movement of a star across the sky caused by its motion through space. Parallax repeats with Earth's orbital cycle, while proper motion accumulates steadily. By observing stars over time, Gaia can distinguish the two patterns and determine distances for stellar samples. Very bright Cepheids can be challenging for some astrometric instruments because detector behavior changes near the brightest limits, but specialized observing strategies and calibration procedures extend the geometric scale to many useful variables. The Hubble Space Telescope has also measured parallaxes for selected Cepheids using spatial scanning techniques. Combining independent parallax programs helps reveal possible zero-point offsets, which are small systematic shifts affecting the reference point of the entire parallax scale. A second geometric route comes from detached eclipsing binary stars. These are systems containing two stars orbiting one another without strongly exchanging material. When the orbital plane lies nearly along the line of sight, one star periodically passes in front of the other. The combined brightness decreases during each eclipse. Precise measurements of these light changes together with spectroscopic observations of the star's orbital velocities allow astronomers to determine their radii temperatures, masses, and physical separation. The physical sizes of the stars can then be compared with their apparent angular sizes or surface brightness. This combination yields a distance to the binary system through geometry and well-tested stellar atmosphere relations. Large samples of detached eclipsing binaries in the Large Magellanic Cloud have produced a precise distance to that galaxy. Because the cloud contains many Cepheid variables, this measurement becomes a powerful anchor for the Cepheid period luminosity relation without depending on the parallax of every individual Cepheid. The geometry of eclipsing binaries is valuable because the orbital motions are governed by gravity and can be reconstructed from observations. Their atmospheres, temperatures, reddening by dust and surface brightness relations introduce uncertainties. Yet these uncertainties differ from those affecting parallax, so agreement between the two methods provides an important test of the absolute distance scale. A third geometric anchor exists far beyond individual stars. In a small number of galaxies, water molecules near a supermassive black hole produce microwave emission through a process called maser amplification. A maser is similar in principle to a laser, but operates at microwave wavelengths. Under suitable physical conditions, populations of water molecules amplify radiation at particular frequencies. The resulting emission can be bright and concentrated into narrow spectral features. Some water megamasers arise in thin disks of molecular gas orbiting central black holes. When the disk is viewed nearly edge-on, different regions move toward or away from Earth at different speeds. Radio telescopes can measure these velocities through Doppler shifts and can also map the angular positions of individual maser spots with very long baseline interferometry. This technique combines widely separated radio antennas so that they act like a single instrument with fine angular resolution. The orbital structure provides a geometric distance. Maser clouds on different sides of the disk reveal the rotation speed around the central mass. Other maser features show measurable accelerations as their orbital velocities change along the line of sight. By comparing angular separations on the sky with physical orbital speeds and accelerations, astronomers can determine the actual size of the disk and therefore its distance. The method does not require a standard candle and can operate at distances far beyond ordinary stellar parallax. The galaxy NGC 4258, also known as Messier 106, contains one of the best studied megamaser disks. Its geometric distance has become an independent anchor for the local distance ladder because the same galaxy also contains Cepheid variables. The maser distance fixes the physical scale, and the Cepheids observed there connect that scale to the population used in supernova host galaxies. Megamasers can also measure the Hubble constant more directly. When they occur in galaxies sufficiently distant, that cosmic expansion dominates over local peculiar motion. Programs that search for and map these systems use disk geometry to obtain absolute distances and galaxy redshifts to measure recession. The number of suitable systems is limited because the required orientation and master conditions are uncommon, but each successful measurement provides a route that is largely independent of the classical Cepheid ladder. No geometric anchor is perfectly free of systematic uncertainty. Parallax requires a stable astrometric reference frame. Eclipsing binaries require accurate treatment of stellar surfaces extinction and orbital geometry. Megamerser disks require detailed models of warped or slightly non-circular structures and precise measurements of velocities, accelerations, and angular positions. The value of using several anchors lies in the fact that their uncertainties arise from different physical and instrumental sources. When parallax eclipsing binaries and megamersers converge on a consistent scale, the first rungs of the distance ladder become more difficult to shift through any single calibration error. Their agreement does not by itself determine the entire expansion rate, but it fixes the local metric foundation on which brighter distance indicators rest. At this deepest geometric level of the ladder, distance is established through angles, orbital motion, and physical dimensions grounding the local measurement of cosmic expansion in directly observable spatial relationships. Precision cosmology depends not only on bright stars, distant explosions, and geometric anchors, but also on the instruments that convert incoming light into numerical measurements. A telescope records photons through mirrors, filters, detectors, and electronic systems, each of which can introduce small effects. When the desired accuracy is only a few percent or better, tiny calibration differences become scientifically important. The local distance ladder therefore includes a hidden layer of work in which astronomers test whether measured brightness, color position, and variability are being recorded consistently across instruments and observing conditions. Photometric calibration establishes how detector counts are translated into physical brightness. A detector does not respond equally to every wavelength, and its sensitivity can change slowly with time. Filters transmit some wavelengths more efficiently than others. Calibration programs observe standard stars and internal reference sources so that these effects can be measured. The goal is to ensure that a star observed in one part of a detector or during one observing campaign can be compared reliably with the same kind of star observed elsewhere. Repeated observation of the same targets also helps reveal whether an apparent offset follows the sky, the instrument, the observing date, or the analysis method. A genuine astronomical signal should remain consistent when these pathways change, while an instrumental bias may shift with them. Small offsets matter because the distance scale depends on brightness differences. If a calibrated standard candle appears slightly brighter than it should, its infrared distance becomes too small. If it appears slightly fainter, the infrared distance becomes too large. These shifts can propagate through several rungs of the ladder. Independent reductions of the same data are often compared to determine whether different software choices produce consistent result. Detector nonlinearity is one example. Ideally, twice as many incoming photons should produce twice as much recorded signal. Real detectors can depart slightly from this behavior, especially when comparing very bright, nearby calibrators with faint stars in distant galaxies. If the response changes with signal level, a calibration established from bright stars may not transfer perfectly to faint ones. Repeated observations across different brightness levels help measure and correct this effect. Crowding creates a different problem. In a dense stellar field, light from neighboring stars can overlap the image of a Cepheid or red giant. At large distances, stars that are physically separated by many light years may fall within nearly the same apparent image area. Their combined light can make the target look brighter than it truly is. This blending would bias the infrared distance downward. High-resolution space telescopes reduce the problem, but they do not eliminate it completely in the most crowded regions. Astronomers test crowding by inserting artificial stars of known brightness into real images and then recovering them with the same analysis pipeline used for actual observations. The difference between inserted and recovered brightness reveals how the surrounding stellar background affects measurement. Observations of the same field with instruments of different resolution provide another check. When Hubble and Webb measure overlapping samples, agreement between their infrared stellar brightnesses limits how large a hidden crowding bias can be. Dust changes measured light in another systematic way. Interstellar grains absorb and scatter shorter wavelengths more strongly than longer wavelengths. A star behind dust therefore appears fainter and redder. If the amount of extinction is underestimated, its distance may be overestimated. Multi-wavelength observations help separate intrinsic stellar color from reddening. Infrared measurements are especially valuable because dust has a weaker effect there, though calibration and stellar atmosphere behavior still require careful treatment. Dust properties are not perfectly identical in every galaxy. Analyses therefore avoid assuming that one simple dust law must describe every environment exactly. They test alternative extinction prescriptions and compare results obtained from different wavelength combinations. Metallicity introduces a related but distinct influence. Stars with different chemical compositions can have slightly different temperatures, colors, and luminosities, even when they share similar pulsation periods or evolutionary stages. Cepheid relations therefore include terms that account for composition. Red giant branch calibrations also use color or metallicity corrections because the luminosity of the tip changes somewhat with stellar population. Spectroscopic observations and stellar population models help estimate these effects. Selection effects enter when the objects that are easiest to detect are not fully representative of the underlying population. At greater distances, brighter Cepheids and supernovae are more likely to be discovered than fainter ones. A survey limited by sensitivity can therefore favor intrinsically luminous objects. If this bias is ignored, distance estimates can shift. Modern surveys model detection efficiency by simulating artificial sources and measuring how often they would be found under real observing conditions. Supernova surveys face additional selection effects because discovery depends on observing cadence, weather, telescope, depth, host, galaxy brightness, and the timing of the explosion. The probability of detecting a supernova can vary with redshift and intrinsic luminosity. Statistical analyses incorporate these selection functions and test whether corrected samples reproduce the distributions expected from simulations. Host galaxy properties are also examined. Type Ia supernova. Brightness after standardization shows small correlations with characteristics such as host stellar mass and star formation environment. These relationships are modeled empirically because a subtle environmental dependence could affect samples differently at different distances. Cepheids are checked for crowding, local surface brightness, metallicity, and period distributions in the same spirit. Calibration uncertainty is therefore not represented by one correction applied at the end. It is a network of small tests woven through the entire analysis. Each potential effect is measured where possible, varied within plausible limits, and propagated into the final uncertainty. Independent teams often make different choices about data selection, calibration, anchors, stellar samples, and statistical methods. Agreement across these choices strengthens confidence, while persistent differences identify places where further work is required. At this instrumental layer, the Hubble tension becomes a test of whether many small biases could collectively imitate a larger cosmological discrepancy. No single known calibration effect has yet been shown to remove the disagreement while remaining consistent with the full set of observations. That conclusion does not make systematic error impossible. It means that any successful explanation must fit numerous cross-checks across wavelengths, detectors, stellar populations, geometric anchors, and supernova samples. The expansion rate therefore rests not only on distant objects, but on the careful measurement of how every recorded photon is translated into distance. Beyond the traditional distance ladder, several methods attempt to measure cosmic expansion without using the same sequence of geometric anchors, Cepheid variables, and calibrated Type Ia supernovae. These approaches are valuable because their uncertainties arise from different physical processes. If they eventually reach comparable precision and agree with one side of the Hubble tension, they can help identify where the disagreement originates. At present, most remain less precise than the strongest early universe and local ladder measurements, but they provide increasingly important independent tests. One major method uses strong gravitational lensing. According to general relativity, a massive object bends the path of light passing through the curved space-time around it. When a distant quasar lies behind a massive foreground galaxy, the galaxy can act as a gravitational lens. Light from the quasar may travel along several different paths around the foreground mass, producing multiple images of the same distant source on the sky. The paths are not identical in length or gravitational environment. Light traveling along one route can therefore arrive earlier than light traveling along another. Quasars naturally vary in brightness as matter falls towards their central supermassive black holes. When the same fluctuation appears in one lensed image and later appears in another, astronomers can measure the time delay between the paths. These delays contain information about the geometry of the system and about cosmic distances. The method is known as time delay cosmography. The measured delay depends partly on the expansion rate because cosmological distances scale with the Hubble constant. It also depends on the distribution of mass in the foreground lens galaxy. Stars contribute to that mass while dark matter provides an additional component extending beyond the visible galaxy. Matter elsewhere along the line of sight can also alter the lensing geometry slightly. Accurate lens modeling is therefore essential. Astronomers use the positions and shapes of the multiple quasar images, the extended light of the quasar's host galaxy, and measurements of stellar motions within the lens galaxy. These observations constrain how mass is distributed. High-resolution imaging from space telescopes and detailed spectroscopy from large ground-based telescopes improve the reconstruction. A central difficulty is the mass sheet degeneracy. Different distributions of lensing mass can reproduce very similar image configurations while implying different time delay distances. Stellar kinematics help reduce this freedom because the motions of stars respond to the gravitational potential of the lens galaxy. Modern analyses, therefore, combine lensing data with increasingly detailed measurements of stellar velocity dispersion and with information from populations of similar galaxies. Earlier strong lensing analyses often favored relatively high values of the present expansion rate broadly closer to local distance ladder results, more conservative treatments that allow greater freedom in lens mass profiles produce wider uncertainties. Current work continues to refine these models with improved imaging and stellar kinematics. Strong lensing remains independent of Cepheid calibration, but its final precision depends on how well the foreground mass distribution can be understood. A second independent route comes from gravitational waves. When compact objects such as neutron stars or black holes orbit one another and merge, they create ripples in space-time. The shape and amplitude of the gravitational wave signal contain information about the mass's orientation and distance of the source. Under general relativity, the waveform provides an absolute luminosity distance without requiring a chain of standard candles. For cosmology, such an event can act as a standard siren. The term describes a gravitational wave source whose measured signal provides distance in a way analogous to how a standard candle provides distance through light. To determine the Hubble constant, the distance from the gravitational waves must be paired with information about the redshift of the source. The binary neutron star merger, detected in August 2017, provides the first major demonstration. Gravitational wave observatories detect the merger while telescopes identify electromagnetic radiation associated with the same event and locate its host galaxy. The gravitational wave signal provides a luminosity distance and the host galaxy provides a redshift. Combining the two produces an expansion rate estimate independent of the conventional stellar distance ladder. The uncertainty from a single event is large. gravitational wave amplitude depends on both distance and the orientation of the binary system. A system viewed nearly along its orbital axis can resemble a more distant system with a different inclination. Electromagnetic observations of the material and jets associated with some mergers can help constrain orientation, improving the distance estimate. Local motions of host galaxies must also be considered because nearby galaxies do not follow the smooth cosmic expansion perfectly. Some gravitational wave events have no identified electromagnetic counterpart or unique host galaxy. These are often called dark sirens. Their distances still come from the gravitational wave signals, but their possible redshifts are estimated statistically using galaxies within the localization region. Many possible host galaxies may contribute to the calculation. As larger samples accumulate and galaxy catalogues improve, the combined statistical information can gradually narrow the allowed expansion rate. Gravitational wave methods have important advantages. Their distance scale is rooted in relativistic waveform physics rather than stellar luminosity. They therefore avoid Cepheid metallicity, corrections, supernova calibration, and much of the ordinary photometric ladder. Their uncertainties are instead associated with detector calibration, source orientation, waveform modeling galaxy catalogues, redshift, completeness, and peculiar velocities. Other independent techniques also contribute smaller pieces of information. Some use the physical sizes and brightness fluctuations of unresolved stellar populations. Others rely on particular properties of galaxies or on cosmological age measurements. Each carries its own astrophysical assumptions and currently has different levels of precision and maturity. Their greatest value comes from comparing routes that do not share the same dominant systematic effects. Because each technique responds differently to distance, matter, and motion, repeated measurements across separate systems are useful for identifying biases that might remain hidden within any single observational method. No single independent method has yet become precise enough to settle the Hubble tension by itself. Strong lenses provide geometrically sensitive distances but require careful mass modeling. Standard sirens provide absolute gravitational wave distances but still have limited event samples and broad uncertainties. Together, these methods widen the network of tests around the expansion rate. The Hubble constant is no longer approached through only two opposing routes. It is increasingly surrounded by independent measurements whose future agreement or disagreement can reveal whether the tension arises from calibration, cosmological modeling, or a combination of effects. The Hubble tension is statistical before it becomes theoretical. It appears when two carefully measured ranges for the present expansion rate overlap less than expected if they are describing the same underlying quantity within the same cosmological framework. One range is inferred mainly from early universe observations interpreted through the Standard Model. The other is obtained from the local distance ladder, where geometric anchors calibrated stars and type Ia supernovae establish an absolute distance scale. Their central values differ by several kilometers per second per megaparsec, while their quoted uncertainties are much smaller than that separation. The early universe value is commonly near 67 to 68 kilometers per second per megaparsec, when cosmic microwave background data and related standard ruler information are interpreted within the standard lambda cold dark matter model. Local Cepheid-based distance ladder analyses commonly lie near 73 kilometers per second per megaparsec. The difference looks modest when written as two numbers, but cosmological measurements have become precise enough that a difference of only several units is difficult to absorb within their estimated uncertainties. Uncertainty does not mean that astronomers simply do not know the answer within some broad interval. Each measurement has a probability distribution describing which values are more or less compatible with the data and assumptions. Statistical uncertainty arises from finite samples, measurement, noise, and a random variation. Systematic uncertainty arises from effects that could shift many measurements in the same direction, such as calibration, offsets, stellar population differences, detector behavior, or assumptions in a cosmological model. Modern analyses attempt to estimate both types and propagate them into the final result. A common way to describe disagreement is through standard deviations. A standard deviation is a measure of the width of an uncertainty distribution. If two independent estimates differ by much less than their combined uncertainty, their apparent disagreement is not surprising. If their central values are separated by several combined standard deviations, random fluctuations become a less satisfactory explanation. Depending on exactly which data sets and calibrations are compared, the Hubble tension has often reached a significance of roughly 5 standard deviations or more for the most precise Cepheid-based distance ladder against the standard model prediction from early universe data. That significance is not a universal property attached permanently to the tension. It changes when data sets, assumptions, calibrations, or statistical treatments change. A measurement with a larger uncertainty can produce a lower formal tension, even if its central value remains almost unchanged. Two methods with partially shared data cannot always be treated as completely independent. Correlated uncertainties must therefore be considered. The statistical question is not simply how far apart two numbers appear, but how their full probability distributions were constructed and how much information they share. This distinction becomes important when alternative local stellar calibrations are included. Some analyses using the tip of the red giant branch or J-region asymptotic giant branch stars have produced central expansion rates closer to the lower range, while others have produced values nearer the Cepheid result. Their uncertainties have generally been larger than those of the most extensive Cepheid ladder, As samples grow and methods are recalibrated, the statistical landscape can change even without a dramatic shift in any individual observation. James Webb Space Telescope measurements add a particularly useful test because its infrared sensitivity and angular resolution allow stellar distance indicators to be examined under different observational conditions from Hubble. Cepheids, red giant branch stars, and other stellar populations can be measured in overlapping supernova host galaxies. Some analyses find that Webb observations support the higher Cepheid-based scale and reduce the plausibility of large crowding errors in earlier Hubble measurements. Other analyses combining several Webb-based stellar indicators obtain intermediate values with larger uncertainties. These differences show why the tension cannot be reduced to a single pair of experiments. Intermediate redshift measurements add further structure. Baryon acoustic oscillations from Desi trace the expansion history using the characteristic scale inherited from the early plasma. When that scale is calibrated with early universe physics within the standard cosmological model, the resulting expansion rate remains in the lower range near the cosmic microwave background inference. This consistency strengthens the internal early universe and standard ruler picture, although the calibration still depends on assumptions about the sound horizon. Independent measurements such as gravitational wave standard sirens and gravitational lens time delays currently have broader probability distributions. They therefore provide useful checks without yet supplying a single decisive statistical verdict. As their precision improves, they can become especially valuable because their dominant uncertainties are different from those of both the distance ladder and the microwave background inference. The persistence of the tension is partly a consequence of shrinking error bars. In earlier decades, measurements of the Hubble constant differed widely because uncertainties were large. Improved telescopes, larger samples, geometric calibrations, and better physical models gradually narrowed the allowed ranges. The disagreement becomes more visible because the measurements become more precise, not because the universe suddenly begins expanding differently. Precision also makes hidden assumptions more important. The early estimate assumes a specific cosmological model connecting the young universe to the present. The local ladder assumes that successive distance calibrations transfer accurately from one class of object to another. A discrepancy can therefore indicate underestimated observational uncertainty, an incomplete model, or a combination of smaller effects. Statistics alone cannot identify which explanation is correct. Researchers test robustness by changing data selections. Calibration, anchors, wavelength ranges, supernova, samples, stellar cuts, foreground treatments, and cosmological assumptions. A result that survives these changes gains credibility. A shift that appears only under one narrow choice receives less weight. The aim is not to maximize the numerical significance of the tension, but to determine whether the probability distributions honestly represent all known uncertainty. At this statistical layer, the Hubble tension is therefore neither a single number nor a simple contest between two instruments. It is a structured mismatch among probability distributions built from different regions of cosmic history and different chains of inference. The most precise early universe analyses continued to prefer a lower present expansion rate within the standard model, while the most precise Cepheid supernova ladder continues to prefer a higher one. Several independent approaches occupy the space around them with varying precision. The central challenge is that the disagreement has remained visible as major sources of uncertainty have been examined, reduced, and cross-checked. The pattern persists across multiple observational programs and calibrations. If the Hubble tension does not arise from an unrecognized measurement error, one possibility is that the standard cosmological model is incomplete. Any extension must preserve the model's existing successes while changing the connection between the early and late universe enough to alter the infrared expansion rate. A proposed solution cannot simply raise the Hubble constant. It must also remain compatible with the cosmic microwave background baryon, acoustic oscillations, primordial element, abundances, galaxy clustering, gravitational lensing, supernova distances, and the growth of cosmic structure. One of the most studied possibilities is early dark energy. In these models, an additional energy component becomes temporarily important before or around the era when the cosmic microwave background is formed. Its presence increases the early expansion rate. A faster expansion leaves less time for sound waves to travel through the primordial plasma, reducing the physical size of the sound horizon. If that ruler is smaller than in the standard model, the same observed angular scale in the microwave background can be consistent with a higher value of the present Hubble constant. The additional component cannot remain important for long. If it persisted with substantial density after recombination, it would strongly alter later expansion and structure formation. Many early dark energy models therefore use a field whose energy density rises to a modest fraction of the total around a particular early epoch, and then rapidly fades relative to the dominant components. This behavior can reduce the sound horizon while leaving the later universe closer to the familiar standard history. Early dark energy can ease the Hubble tension in some combinations of data, but it is not an established solution. The same change that reduces the sound horizon also alters the heights and shapes of microwave background features and can affect the growth of matter fluctuations. High-precision measurements from Planck, the Atacama Cosmology Telescope (DAISY), and other surveys restrict the allowed behavior. Some recent analyses still find regions of early dark energy parameter space that raise the infrared expansion rate substantially, while other combinations place tighter limits. The outcome depends on the model and the data included. Another family of proposals changes the amount or behavior of radiation in the early universe. Additional light particles, sometimes described as dark radiation, would increase the early expansion rate. This can also reduce the sound horizon However, extra radiation changes the microwave background and the formation of light elements during primordial nucleosynthesis. Measurements of helium and deuterium therefore place strong limits on how much additional radiation can be present. Neutrinos offer a related possibility because they form part of the relativistic energy content of the young universe. Their masses, number of effective species, and interactions influence the microwave background and, later, structure. Models with unusual neutrino interactions can change how perturbations evolve before recombination, yet laboratory measurements, neutrino oscillation, experiments primordial, nucleosynthesis, cosmic microwave observations, and large-scale structure together restrict the available freedom. Altering neutrino physics alone has not produced or accepted resolution of the Hubble tension. Some proposals modify the process by which neutral atoms form. The infrared sound horizon and microwave pattern depend on the timing of recombination when electrons become bound to nuclei and photons begin to travel freely. Changes in atomic rates, the electron mass fundamental constants, or other recombination physics could shift this timing. Such models are tightly constrained because the microwave background contains information about the width and position of the last scattering region. Any modification must reproduce that structure while also improving the expansion rate agreement. Late-time changes provide a different route. Instead of altering the early sound horizon, they modify the expansion history after the cosmic microwave background is released. The target is dark energy. In the standard model, dark energy behaves like a cosmological constant whose density remains constant as space expands. A dynamical form of dark energy could change with time, altering the relation among redshift distance and the present expansion rate. DeSci measurements have strengthened interest in this possibility. When its baryon acoustic oscillation data are combined with cosmic microwave background and supernova observations, some fits prefer a time-varying dark energy equation of state over a cosmological constant. The preference depends on which supernova sample and analysis choices are used, so it is not considered a discovery of evolving dark energy. More importantly, for the Hubble tension, a better fit to late-time expansion data does not automatically move the infrared Hubble constant far enough toward the local Cepheid value. Dynamical dark energy and the Hubble tension are related questions, but they are not identical. Interactions within the dark sector provide another possibility. Dark matter might exchange energy or momentum with dark energy, or part of the dark matter might decay over cosmic time. Such behavior could alter expansion and the growth of structure. These models add flexibility, but that flexibility must satisfy observations of galaxy, clustering, gravitational lensing, the microwave background, and the abundance of structures. No interacting or decaying dark sector model has yet achieved observational preference as the explanation of the Hubble tension. Modified gravity moves the change deeper still. General relativity describes gravity successfully from the solar system to many astrophysical and cosmological tests, but it remains possible to examine whether gravity behaves differently over cosmic distances or epochs. A modified gravitational law could change expansion and structure growth. The difficulty is that those two effects are closely connected. A model that improves the expansion rate fit may predict gravitational lensing or galaxy growth that conflicts with observation. The pattern across these proposals is one of constrained possibility rather than established replacement. Early dark energy can shrink the sound horizon. Additional radiation can accelerate early expansion. Modified recombination can alter the release of ancient light. Dynamical dark energy can reshape late expansion. Dark sector interactions and modified gravity can change the relationship between matter and space-time. Each mechanism creates additional observational consequences that can be tested. The Hubble tension places a precise demand on new physics. Any successful extension must change enough of cosmic history to reconcile the expansion rates while changing little enough to preserve the many observations already explained by the standard model. Several ideas remain viable in restricted forms, and new data continue to narrow their allowed regions. None has yet become a consensus solution. The unresolved discrepancy remains an invitation to test whether the standard description of cosmic evolution is complete. The Hubble tension now stands at the center of a broad network of observations rather than at the boundary between only two experiments. On one side, measurements of the cosmic microwave background interpreted within the standard lambda cold dark matter model continue to favor a present expansion rate near the high 60s in kilometers per second per megaparsec. On the other side, the Cepheid and Type Ia supernova distance ladder continues to favor a value near the low 70s, with the most precise determinations lying around 73 kilometers per second per megaparsec. The difference is small compared with the expansion rate itself, yet large compared with the quoted uncertainties. The disagreement matters because both routes are built from mature observational programs. The early universe inference rests on an accurately measured microwave sky and on a model that also describes many other features of cosmology. The local distance ladder rests on geometric anchors, pulsating stars nearby supernova hosts and more distant supernovae in the smooth Hubble flow. Each route contains assumptions and corrections, but neither has produced a single confirmed error large enough to bring the two most precise values into agreement. The cosmic microwave background remains one of the strongest pieces of evidence for the standard cosmological model. Its temperature pattern polarization, acoustic structure, and gravitational lensing broadly fit a universe containing ordinary matter, cold dark matter, radiation neutrinos, and dark energy represented by a cosmological constant. Within that framework, the early plasma fixes a sound horizon, and the observed angular pattern constrains the later expansion history. The infrared Hubble constant is therefore precise, because many physical relationships are required to fit simultaneously. The local root is different in character. It does not begin with the young universe and project a model across almost all cosmic history. It establishes physical distances nearby and transfers that scale outward. Parallax eclipsing binaries and water megamasers anchor the geometry. Cepheid variables connect those anchors to supernova host galaxies. Type Ia supernovae then extend the scale into regions where local peculiar motions become relatively small compared with cosmic recession. The resulting expansion rate is measured within the late universe rather than inferred from primordial conditions. Repeated tests have made simple explanations harder to maintain. Higher resolution infrared observations from the James Webb Space Telescope generally confirm that Cepheid distances measured with the Hubble Space Telescope are not shifted enough by stellar crowding to erase the tension. Comparisons among Cepheids, the tip of the red giant branch, and other stellar indicators provide additional tests, although different calibrations and supernova samples can still produce noticeably different central values. The local distance scale is therefore increasingly cross-checked, but not every independent stellar route has reached the same precision or exactly the same result. The early side also receives independent support. Baryon acoustic oscillations trace the characteristic scale inherited from the primordial plasma across